recording.
All right, so we finished yesterday. We did example 3. Today we're starting example 4, but it involves this number e, which is called the natural base. Okay, we have two different ideas here. We have logarithms of base b of a number x, and usually we'll see that as a function. Log base b of x is y. Log base b of x is y. That base could be any number. Most commonly, we see common log. That's why we call it a common log, because most of the time we're in base 10. You see that in chemistry all the time, base 10. Okay. You see that in scientific notation, 10 to the whatever power. Okay, that's log base 10. If that log base, so this number down here, 10, is anything else, you would see it shown, right? If it is log base e of x equals y, that's a special number. And instead of calling it log base e, we switch and we call it the natural log. Natural log of x, sorry, not of e. Natural log of x is y. So this is a way of saying log base e. But if the base is e, we switch gears and we call it the natural log. And the reason we do that is because of how the number e behaves in a logarithmic equation. Are you with me on that? Okay, it's been a while. E is just a number. We use the letter E to represent that number because that number comes up so often that we decided to give it a name instead of calling it 2.71, blah, 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 blah. Okay? It's super irrational. We don't want to round. We don't want to have to recall the decimals. So we gave it a name, E. Like pi. You with me? We use the symbol, Greek letter pi, to represent the number 3.14. Anybody know how we get the number pi? Like what it actually is?
Isn't it like 7 something? There's a 7 in there.
It's the ratio. It's the ratio of circumference to diameter on a circle. It's a ratio. Mm-hmm.
I thought it was like 7 to
Yeah, because it doesn't matter how big your circle is, the ratio of circumference to diameter is always pi. There you go. Okay, anyways, coming back to here, it says example 4.
1, 2 over 7?
22 sevenths, yes, that's pi. 22 sevenths. Okay, focus. Example 4 says the number of bacteria B in a particular culture, so that's like a culture being grown in like a petri dish or something like that, okay? Not culture as in a society, but a culture as in something populating. So the bacteria in the culture can be modeled by the exponential function b of t equals e to the 0.31 t, where t is measured in hours. You following what it's telling us? So this is our function. B of t equals 17 times e to the 0.31. It says let a of t equal a times b to the t. This is an equivalent expression for b of t. Anytime I see this equivalent expression business, you saw this on your homework, this kind of brings back the idea that we had when we were doing lesson 2.4. It's wanting us to realize what's happening with these powers and be able to rewrite the expression in a different form. So right now in the powers up here, we have e to the 0.31 times t. They're multiplying those exponents, right? So that brings up the idea that I could rewrite it. Let a of t equal, a is going to be a, regardless. That number is not going to change. The initial value is still 17. But instead of writing it as e to the 0.31 t, I could write it as e to the 0.31 to the t power. This is going to be an equivalent expression. right? So the idea here is when I'm multiplying my powers, when I'm multiplying these powers, 0.31t, it's the same as raising a power to a power. Okay, so the equivalent expression here is this. A of t equals 17 times e to the 0.31 to the t. Find the value of a.
17.
A is still 17. So A is still 17. The initial value here is the same as the initial value on B of t. We changed the base. So instead of the base being e, now the base is going to be e to the 0.31, whatever number that is. Okay, so my new function, a of t, would actually be 17 times whatever that new number is to the t power. Okay, we changed the base.
So the new number would be
e to the 0.31. You would get a decimal on that. It'd be rounded at best. Okay, the question is, though, what's a? And a is still 17. Cool? So when we manipulate exponential functions, we're not changing the initial value. We're changing the base. Eventually, that might change the initial value. Okay? And I'm just kind of thinking off the top of my head. But if I had something, let's just let it be really basic numbers here. Let f of x equal 7. True, it said 7 times 2 to the x plus 3. Okay? If I were to do a rewrite on this and find an equivalent expression, I might say g of x is equal to 7 times 2 to the x times, right? When I'm adding my exponents, I could have been multiplying like bases. In which case, what's about to happen?
You're about to multiply 7 times.
This is going to be 8, right? So I'm going to have 7 times 2 cubed times 2 to the x, which would be 7 by 8. Now it's 56 times 2 to the x. So that initial value could change depending on what's happening with your function manipulation. In the problem that we're actually working right now, the initial value didn't change because we raised a power to a power and my base got changed. Do you see the difference? Questions on that? Okay. All right, so letter B, it says find the, everybody take your pencil. Take your pencil, wish it was red, underline average rate of change. This is huge. The slope. The slope. It's the change in B over the change in T. Change in the function, B of T, divided by the change in time. Okay, so what do we want to do? We want to find average rate of change. They said it's the slope, so let's use the letter M. Average rate of change. Every time I see that, from the next 79 years of your life, you're going to see this in calculus every day. You're going to see this in physics every day. Average rate of change, that means slope. M equals B of T at T equals 7. So B of 7 minus B of 1. This is how I'm getting y2 minus y1. I've got a function B of t. I want to evaluate that function at x equals 7 or t equals 7 and at t equals 1. So y2 minus y1 over x2 minus x1. What's x2? 7. x1? 1. Whoa. Do y'all see what just happened? We've got a function b of t. That's up here. We want to evaluate it at t equals 7. This is x1, x2. How do we find y2 and y1? We plug in these numbers into our b of t function. Yeah? Okay. It's best if this is already on your calculator. So go on your calculator right now. Everyone participate. And you're going to put that function into y1 on your calculator. Or into f1. Graph it. Put it in your grapher right now.
You know how much I love water. You know, just
Rapid. There are 30 over here that are charged and waiting for you. The function b of t. No. You're not testing with Desmos, big guy. B of t equals 17.
17.
Okay, so finally, we got a quotient. What'd we get?
20.9521.
Okay, so the slope here, the average rate of change, 20.952. Okay, here's the next question. Find the value of t when the number of bacteria in the particular culture is 1,000. So find the value of t when the number of bacteria in the culture is 1,000. Okay, so the question, he says, plug in 1,000. We've got b of t equal to 17 times e to the 0.31 t. Plug in 1,000. So the question then would be, what's the number of bacteria after 1,000 hours? Oh, that's not what it's asking. It wants the number of bacteria to be 1,000. Find the value of t.
So literally a of 1,000 equals.
No, we are not. Listen, everybody listen. It's not b of 1,000. Read the first 3 words here. Find the value of t. First 5 words. Find the value of t. If they wanted me to plug in 1,000 for t, it would say put 1,000 in for t. It wants me to solve for t. When the number of bacteria, b of t, is 1,000. Okay, so we've got 2 different options there. One is plug in 1,000 for t. That would be find the number of bacteria at 1,000 years or 1,000 hours or whatever it was asking, right? That's not what this says. This says find the value of t when the number of bacteria is 1,000. Yeah. So here's our setup. 1,000 is equal to 17 times e to the 0.31 t. Okay, you're going to want to get some room here on your paper. Write this, or if you want scratch paper or someplace else. Okay, you have 2 options. One, you can try to graph the intersection. I see lots of you headed in that direction. That's what they want. They expect you to find where the 2 things intersect. You know that this is going to happen somewhere between, in your y values, somewhere probably between 950 and y equals, we're trying to look for 1,000, so maybe somewhere between 950 and 1050, right? So you could go in and set your window settings in your y direction to be up there. Can we do that? Yeah. I'll show you how in just a minute on your calculator. Okay? Everybody freeze. The problem with that is we don't know where x has to be. This might be my y min and my y max. I know on my calculator on the home screen, I want to be able to see some range between 950 and 1,050 so that my 1,000 might be smack dab in the middle of that and I could see my intersection. Are y'all seeing what I'm saying? You could do that on your calculator, and I will walk you through that process in just a minute. The problem is you don't know what your x boundaries need to be on your window. And honestly, by looking at this, I don't know how you would know. I can't look at that function and tell. Okay? So I have an alternate method for you. Instead of having to hunt and pick and try to find some window that actually holds my solution somewhere in here. Okay? Insolve. Okay.
Insolve with PSCD today, it did not work.
Okay, but Insolve, yes, we're going to solve this equation. Okay? I think solving it is a lot faster than trying to find a window. Okay? But not Insolve. We can actually solve We can solve these by hand. It's not too bad. Okay, so I want to show you how to do that. They don't suggest doing that in these notes, and I think it's a lot easier if we do. Okay, so I want to show you how to solve. Everybody write this function down. Everybody write the function down. We are trying to get t by itself. We are trying to get t by itself. So the first thing we're going to do here is divide by 17. A 1,017ths. Don't simplify. Don't simplify. We're going to use our calculator in just a minute. Okay? Don't worry about simplifying. Just let it be. Let it be. Okay, so we've got 1,017ths equals e to the 0.31 t. Okay? Y'all with me? Yeah, so how do I get up in the exponential business? Natural log. Natural log. Remember that natural log is the inverse of e. So we can natural log both sides, and we can get rid of the e business, and we can bring that 0.31 t down to ground level.
Whoa.
Yeah. The natural log of e is 1. So if I natural log both sides, I'm done with that. So on the left side, now I have the natural log. When you type natural log on your calculator, it opens parentheses. You're going to stick that 1,000 over 17 in the parentheses.
Do we also need to divide by 1?
That's next. We're still going to get t by itself. The only thing left here to do is divide by 0.31. Divide by 0.31. Okay, so t is going to be equal to the natural log of 1,000 over 17 divided by 0.31. That wasn't even gross. And I think that's faster than trying to find a window that fits your intersection. So type on your calculator the natural log of 1,000 over 17 divided by 0.31. 13.14. Okay? So 13.14 seconds. Now, if I was trying to see that intersection on my calculator, now maybe I want my x minimum. What do I want my lowest x value to be? 10. What do I want my highest x value to be?
20 or 15.
How about 15? Okay, so this is a great window setting. This is going to show where that intersection might happen to be. But I had absolutely no idea that I needed to go from 10 to 15 in x. No idea. Okay? I don't know how you're going to know that this is where that intersection is without solving it. Unless you just get in your calculator and you start hunting for some kind of intersection there. Okay? So I'm going to pause the recording really quickly so that I can... Okay, so we're done with the calculator portion of that. You have to know the difference between plugging in 1,000 and setting it equal to 1,000. Okay? Our answer here, when we solved for t, was 13.14. Is it hours?
Seconds.
Is it seconds? I think it's hours.
It is ours, my bad.
Hours. I think we're measured in hours. Okay, example 5, moving on. After 50 deer were introduced to a large wooded area, the population of deer in the wooded area can be modeled by the exponential function d of t equals a times b to the t, where t represents the number of years since deer were first introduced to the wooded area. The population of deer increases by 13%. That's a percentage. That cannot go into an exponential equation as a percentage. It's also increasing. We talked about this last year. If I'm going to increase by 13%, then I'm going to add 1 plus 0.13 as my growth rate. 1 plus 0.13. Remember that 13% gets turned into a decimal. Bop, bop. Okay, so you're taking 13% and you're moving that decimal to the left to make it 0.13. And then if it's an increase, you're going to add 1. If it's a decrease, you're going to subtract it from 1. right? It's like change at the concession stand. I owe you 13 cents. That's 1.13. You paid $1 and I'm keeping 13 cents. What are you getting back? 87 cents. Okay? If it's subtracting, you do 1 minus that percentage, and that's what number you put in the hole. Okay? Find the values of A and B and use these values to write an expression for D of T. So A is going to be our initial population of deer. What does it tell us? 50. Put 50 deer in the woods. And B, our growth rate is 1.13. It's growing. Again, if it was decreasing by 13%, our B would be 0.87. You'd do 1 minus that percentage. Write the equation for D of T. D of T equals 50 times 1.13 to the T power. After 50 deer, we're put in the woods. Okay, introduced. So starting. According to the model found in part A, what's the population in the large wooded area after 6 years? So plug in 6 to your function. We're trying to find D of 6. The other question would be, what is T when there are 6 deer in the woods, right? If they wanted you to set it equal to 6, that's what they would have said. They want to know how many deer are in the woods after 6 years. 50 times 1.13 to the 6th is 104.098 deer. I'm going to round to the nearest hundredth because I don't want to imagine partial deer. It's fine. Some antlers left behind during season. Okay. All right, letter C. Letter C. Find the time T when the population of deer is expected to reach 5,000. Find the time T when the population of deer is expected to reach 5,000. So now I'm looking for T. I have to set my equation equal to 5,000. So 5,000 equals 50 times 1.13 to the T power. And again, we're going to have to solve, but this time I'm not in base E. So everybody pay attention. We've got 5,000 equal to 50 times 1.13 to the T power. We're going to solve it, but I'm not in base E, so I'm going to have to use a log instead of the natural log. Divide by 50 first. You can reduce it. You can let it be 500 over 5. Equal to 1.13 to the T power. You're going to log it because you can't natural log if there's not a base E. So you're going to log both sides. Now we're in base 10. It's automatic base 10. When I log both sides, what does that allow me to do with the T? It brings it down to the front. So now this is T times the log base 10 of 1.13. It's fine. Huh? Okay, so what I did is now on this right side, I have log base 10 of 1.13 to the T power. Not to the 2, to the T power. The rule is on logarithms, when the argument is raised to the power, that's the same thing as writing the power in front as a coefficient. Yeah, so now you're going to divide both sides by log base 10 of 1.13, and you get T. I got 37.6. 37.68. And these are what? Years. This is how many years after they were introduced would the population equal 5,000?
On the test, do we have to specify the 10? Because if it's natural, why would we have to specify it?
It's not natural. It's not natural. Oh. On your calculator, you have to tell it you're in base 10. You can be in whatever base you want to.
On the test, you can just leave it like log without 10.
If you don't write the 10, it's automatic 10.
So
Yeah. All right, we'll stop there. We have our whole section 5 homework tomorrow. Okay? Yeah.